Welcome to the Explainer. We're going to tackle a question today, one that seems so simple, right? But the answer? It might totally change how you look at the sky.
Okay, so let's get right to it. Why is a rainbow curved? I mean, you probably think you know the answer. It's one of those things we all learn in science class, a neat little fact. But what if that answer, the one we've all known for years, is just wrong? You know the textbook explanation, right? It's all about geometry, something about a very specific 42-degree angle between the sun, a bazillion tiny raindrops acting like little prisms, and your eye. And poof, they all come together to make that perfect curve. It's a theory that's been the gold standard for centuries. But here's where things get interesting. Our source for today, an article by Mathis, says that this 380-year-old explanation isn't just a little off. He says it's completely wrong. He argues the real answer has been staring us in the face this whole time. All right, so before we blow the whole thing up, let's do a quick refresher on the official story. This is the one that goes all the way back to René Descartes, way back in 1637. So the standard model, this cone of vision thing, it says you see a curve because a rainbow isn't just a 2D arc. It's actually the base of a giant 3D cone of light, and your eye is right at the pointy tip. The only raindrops you see are the ones on the edge of that cone, and that's what makes it look like a circle. And the process for how this happens is supposed to be simple. Step 1, sunlight goes into a raindrop. Step 2, it bounces off the back. Step 3, it comes back out, bending and splitting into all those amazing colors. The key part, the really crucial part, is that this light has to hit your eye at exactly 42 degrees for red. It sounds super neat and tidy, but is it right? Okay, so this is where our source starts poking holes in that neat and tidy story. The author says, hey, this theory sounds great on paper, but it just doesn't line up with what we actually see with our own eyes. Think about this for a second. This is a big one. If the rainbow really depends on your precise position, your own personal cone of vision, then shouldn't it move when you move? Like, if you walk to the left, shouldn't it shift against those trees in the background? But it doesn't. It just stays put, almost like it's painted on the sky. And here's another thing that just doesn't add up. The whole theory is based on millions of tiny raindrops, right? But what happens in a storm? The wind is howling, those drops are getting blown all over the place, yet the rainbow is this perfectly stable, solid arc. It's not flickering or waving around. How does something so chaotic create something so perfect? And then there's the double rainbow. You've seen it, right? What about that dark, kind of spooky-looking gap between the two bows? It's called Alexander's band. The author argues that the official explanation for this is maybe the shakiest part of the entire theory. They just say, oh, that's just a spot where no light gets to your eye. So after picking apart the old model, the author doesn't just leave us hanging. Nope, he offers up a totally different theory. And it's pretty radical. It basically flips everything we thought we knew about rainbows completely upside down. Okay, get ready for this. The new theory is, a rainbow isn't an optical illusion made by raindrops. It's a picture, a rear-projected image of the sun itself, thrown onto a giant screen of mist in the air. So why is it curved? Because the sun is round. It's that simple. This quote from Mathis really gets to the heart of it. It is the bands of dark and light that cause the rainbow, not the rainbow that causes the bands. What he's saying is, the structure comes first. Those bands of light and dark are the real thing. They're the image of the sun. The pretty colors? That's just what happens when that image gets projected onto the rain. Okay, so a wild theory is one thing, but you need evidence, right? Well, this is where it gets really compelling. The author says to forget about the raindrops for a minute and let's look at the sun. He says, look at a double rainbow. You've got a bright inner arc, then that dark Alexander's band, then a fainter outer arc. Now look at the sun's atmosphere, its corona. It has layers, a bright inner part, a cooler, darker middle layer, and a fainter outer layer. He's saying the rainbow is a literal snapshot of the sun's own layered structure. And here's the real bombshell. The author actually measured photos of both, and he says the proportions are a perfect match. The width of that dark band in the rainbow, compared to the rainbow's size, is the exact same ratio as the dark layer in the sun's corona. He says that's not a coincidence. It's proof. One is a picture of the other. And check this out. This photo really drives the point home. It's a rainbow over a waterfall. And see that? It just stops. right at the shadow on the rocks. The old theory has a really hard time with that. It should just kind of fade out. But with the projection theory, it makes perfect sense. The sunlit mist is the movie screen. You turn off the screen, and the movie's gone.
Okay, so let's put these two ideas side by side and see how they really compare.
I mean, look at the difference here. The standard model, the curve is an illusion unique to you. The new theory, it's a real image of the sun. For the role of rain, the old model says it's millions of little prisms. The new one says it's one big projection screen. And Alexander's band, wow, it goes from being a weird gap in the light to an actual picture of a layer of the sun. These are two totally different worlds.
So, that leaves us with a pretty cool question, doesn't it? The next time you see a rainbow, what are you really looking at? Is it an optical trick created by your own eye and a bit of geometry? Or are you looking at a giant, beautiful portrait of the sun projected right there in the sky for you to see? It definitely makes you think.